Banyaknya recording tak jadi. So this is tutorial number 7. Wind flows past a semicircular shape concept heart which was prefabricated using lightweight corrugated galvanized steel. The radius and length of the heart are 4 meters and 18 meters respectively. Determine the force tending to topple the heart of its foundation. If the wind of density is 1.25 kilogram per meter cube, flows at speed of 24 kilometer per hour. In real fluid flow problem, how will the strong wind topple up the heart of its foundation? Briefly explain your answer. So here the concept heart is actually the semicircular heart like this one. Okay, so in this situation, we know that the R here is equal to 4. I'm sorry, so 4 here. So, and the length here is 18 meters. So, and then you have a linear flow like this one. So, this is a linear flow. So, and then you must know that normally people will take linear flow in negative direction because psi combination will have will equal to 0. So here, what you need to do is you need to imagine that now it's actually you are doing the flow around cylinder. So how to differentiate between this half cylinder, it depends on the value of our integration. So for this situation, we use from 0 to pi. So this is 0 and this is pi. So this is the difference between full cylinder and half cylinder like this one. So because we need to calculate about the force, so we are using the lift force here. So the calculation is F dF sine theta d theta. Why? Because the question asks us about the force that could leave the heart. So we substitute the value of F here by substituting the value of pressure and area here. So we have a sine theta and theta as a in here. So and then in this situation, we could take the P1 is equal to P ATM because let's say we have a heart here. So we have a linear flow here. So here, point number 1. So here, the pressure is P ATM. And we assume that P ATM here is equal to 0. And we take the value of A here is L times R. Why? Because we have a force, a velocity here, and the area here, okay, the projection area. So projection area means we have an object like this one. And then when we put a light here, source of light, so the shadow is actually just give us a rectangular area. So this rectangular area is called the projection area. Okay, so the projection area for this calculation is L times R. So we substitute all this value into this equation. So we have this equation. So we could simplify it as this one. Okay, because all of this term is nothing to do with theta. So we do the integration only for parameter that has theta. So and then to simplify this one, so we substitute the value of sine theta with 1 minus cos square theta. So and then we could simplify it as this one. So the trick is because if we have this kind of terms, we could do the assumption as if x is equal to cos theta, so dx will equal to negative sine d theta. So what we do is we substitute the value of cos here and also sine theta here with x and dx. So because we already changed the term, we assume that cos theta and sine theta with certain value. So means that the The limit is also need to be changed. So we change it like this one. So at 0, cos theta will give us 1, and at pi, cos theta will give us -1. So means we need to change 0 and pi here with 1 and -1. So we change the term. So we have 4x squared minus 3 and negative dx, and then we could do this integration. So and then when we do this integration, so we could have this term. So after we substitute with limit 1 and -1. So and then when we substitute all the values, so please make sure that you convert this value 24 kilometer per hour with SI unit, so it is become 6.6 meter per second. So you could calculate that lift force is actually occur is 6.6 times 10 by the power of 3 Newton. In real fluid flow, the drag force effect need to be considered. In calculating the net force tend to topple the hut. This is because the actual pressure distribution over the real portion of the hut is not modeled correctly by potential flow theory alone. So this statement is saying about, so we have an object here. So and then we have a linear flow here. So this linear flow will create lift force. Why? Because you know that the velocity is higher at this location. So higher velocity will give us a low pressure. So a low pressure here means the pressure inside the tank is higher to the pressure at this location. So it has potential to be lifted. Okay. However, in real situation, when you have a flow here, so you will have two types of force, which is one is lift force, and another one is the drag force, mean the resistance that occur at this situation. So in real force, you need to balance the lift force and the drag force. If the drag force is maybe higher, it's maybe reduce the value of lift force. So means that the total flow or the total force is actually cannot leave the tent. So this is uh, the real situation. So however, in ideal flow, we assume that there are no resistance. So if the flow has no resistance, means that the drag force is not exist. So this is tutorial for ideal flow number 8. So what do you understand about vorticity? So if velocity component is given as shown below, so show that vorticity can be written as this one. Okay, so here please make sure that you still remember the value of lambda and so on and so forth. So this is the nabla. So we learned about nabla in our chapter 1, the differential method. So vorticity is circulation per unit area. So we are doing about the first question is about the vorticity, and the velocity component is given like this one. So and then vorticity is circulation per unit area, and it is shown as zeta. So this is zeta equal to the gamma over dA. So you may write as gamma over dA, okay, for the total amount. So it's depend on you, it depend on the textbook here. So the way we could calculate the value of zeta is by we imagine that we have a molecule here, and this molecule is actually travel at this direction to this direction to this direction, and then come back into its original condition. So what we need to do is we just calculate by using the idea of circulation. So circulation is, so gamma is u times L. The u here is the velocity, but the L here is the distance traveled by the molecule. So means that if you have a molecule here, so you need to know what is the velocity and what is the distance it's traveled to this on this path. And also you need to know what is the distance here and what is the distance here, and also what is the distance here. Okay, so and then we could write like this one. So you have a UR d theta plus U theta plus du theta, R plus dr d theta, and then you have this one and you have this one. So I already discussed this in my notes. You may see a video about it. So this is just the answer for this circulation from this diagram. So you may also write a diagram as simple as, for example, for the U is V plus dV and dr. It is okay to write as this one. So and then we could substitute into this equation. So zeta is equal gamma over A. So we have the d gamma here. So and then we divide into the A here. So A here, it is okay for you just to imagine that we have here is r d theta and the length here is dr. So that's why we only have r d theta and dr as our area. So this is the assumption in this calculation. So if you do this mathematical here, you will get this one is the vorticity of ideal flow. So and then we substitute the value of u theta and also ur here with what we have here. So and then we could get this term. So and then this term is actually shown as negative nabla square psi. So I hope you could do this at home and try it by yourself. Okay, this is tutorial number 9. The component velocity for flow around cylinder is given as shown below. So it gives the question gives us the value of UR and also the value of U theta here. And this here it gives you flow around cylinder. Okay, but when you see the velocity components here, you will find that we have a gamma element here. So means that the existence of gamma here will show us that this is actually the rotating cylinder. Okay, please be careful about this. And I hope you alert that these two velocity component is actually not the same with the tutorial. So means that it is not simply just like this motion. Okay, maybe it's show a different type of motion. So please do not assume that all velocity component is the same. So it may be slightly different. Okay, so and then what we need to calculate is first we need to determine the stream function. So and then we need to show it is a irrotational flow, because in ideal flow we only could solve an irrotational flow. Please make sure that you understand that. And then coordinate of stagnation point is gamma is equal to pi r. And also you need to sketch the stream line. Okay, first we need to calculate the stream function. You know that if we have component velocity, we are able to calculate the stream function. So we use the idea of Cauchy-Riemann equation. So we have UR is equal to d psi over r d theta, and this is the value. So what we need to do is we need to integrate the d psi here. So first you need to bring the d theta to the right side, and then you integrate both sides. So finally you will get this one. But this is not a final answer because you have an integer as constant here, and also constant that came from fr, means function of r. So from boundary condition, we could say that the value of C here is equal to 0. Then we could neglect the value of C, but we cannot simply neglect the value of FR. Please do not simply neglect the value of FR. So, and then what we need to do from here is we differentiate with dr, because we want to find what is the value of FR here. So if we differentiate with FR, it is equal to u theta, and then we could substitute or we could equalize with the value of u theta given from the question. And then what we could do here is we could integrate this term both sides. So we have this term. Okay, so here, okay, I just show you another method. So for example, and here we have a constant here, C, and also a constant that came from F theta. Okay, you could see the relation here. Here we do the integration in terms of d theta, then we will have constant of Fr. So here we do the integration in terms of dr, then we could get the constant in terms of theta. So, and then what we do? So in sometimes this method can be used, but I still prefer that you calculate the value of, you do the calculation to get the value of Fr. So here you need to compare the psi that you get from the theta and psi that you get from the r function. So you will find that in psi calculated by using the theta component. So you have this term, and this is the term for psi that you calculated from the radius term, the ur term. Then you could find that from here you will find that this term, okay, this term, okay, is actually reflect to this one actually. Okay, it also appear at this one. Okay, so and then the Fr here, okay, it maybe reflect the value of R at this term. Okay, so from this comparison, we could say that, so actually when we combine these two equations, so we could write its resultant equation as negative ur 1 minus r square cos theta here, and negative gamma over 2 pi ln r and c. And then if we substitute the value of r is equal to r here, so this is the final stream function that we need to use. Okay, so and then, okay, so at this moment, you cannot leave the value of c, okay, because we need to calculate what is the constant value of c. So what we need to do is we substitute the value of r equal r, and then we get that the value psi is equal to 0. So, and then if the psi is equal to 0, so we substitute the 0 here, so we could get c is actually pi over 2 pi, gamma over 2 pi ln r, ln capital R. So we need to substitute this value into this term. And finally, what we get is, if you substitute the value here with gamma over 2 pi ln r, so finally you will get these terms. Okay, so what is the difference between this solution with the previous solution that I already discussed with you? In this solution, we just use the value here. Okay, in this solution, you know that we have a gamma here. Okay, so and then we know that the gamma here is actually showing the rotating cylinder. And the second one is because we use the idea of comparison between these two terms. So if you do the first method that I teach you in in previous tutorial, so for example, you just substitute the value of you need to substitute the value of constant, the boundary condition. So you maybe get the value C is equal to 0, and then you finally get the value of FR here. So you may have this term immediately. So this is the final term that you have. Okay, so here, okay, so means that yeah, you need very careful when to choose your method here. So this is the stream function for this situation. So again, I hope you could remember, because in a rotating cylinder, both conditions. So this is about the doublet and linear. This is about the vortex. So vortex needs to have some term of R over A. So you cannot just leave it as ln R here. So it must be R equal A, or in this situation we have R over capital R, because in this question they assume that the radius is equal to capital R. In my notes previously, we assume that the value of R is equal to A, then we substitute the value of capital A here. So I hope you need to understand what you did, not just remember all the solution. So and then if we want to prove it, it is an irrotational flow. So we already have two methods. If you want to do this method, so okay, it's in previous tutorial we have this kind of solution. So let's say I start with this equation. So what we need to do is, because we already have psi here, so and then we could differentiate the value of psi of this one, all of this, and then we substitute into the equation. So we found that the value is equal to 0, means that the flow is a rotational flow. So I hope you could try this at home to make sure that you know how to derive all of this. And then the coordinate of stagnation point, if gamma is equal to pi r and r is equal to capital R. So we know that when we calculate or we discuss about stagnation point, so the rule of thumb is u theta and u r is equal to 0. So what we need, so and then we assume that u theta is equal to 0, and this is the term of u theta. And then we substitute the value r equal capital R and gamma is 2 pi r. So finally we could get cos theta is equal to negative 1 over 2u. So we assume that u is in positive direction, for example, to simplify this one. So we could get that theta is cos reverse theta of negative 1 over 2u, and negative cos and negative reverse theta negative 1 over 2u. So from this, we could imagine that the stream function is actually like this one. Okay, why? Because if you see this, for example, we just imagine that u is almost positive. Okay, so if we imagine that u is positive, so means that you need to calculate what is the value of negative cos. So you have a negative here. So and then if you calculate this one, you will find that it is occur at this and this point. So and then I hope you could draw a stream function. So you have a flow like this one, and then it goes on the surface, and then it flow out like this one, and then the next streamline is showing like this. So this is an example of a streamline, okay, that you need to draw after you calculate all the values. So here you need to show an arrow here to let people know at what direction the flow flows. So and then you need to show clearly a stagnation point. So means that you need to draw a stagnation point very clear on the surface, on the cylinder surface. Okay, please do this very well, then you will get a full mark for this question.